So in the end, we got to multiply this thing by 1,000. No, yeah, by 1,000 times 1,000. So we do that, and then so this is really 28.6. 28.6 grams per mole.
28.6?
28.6. And so if we work that out, then our total really is 61.9 grams per mole. Okay? So that's our AMU.
This is not going to be in the test, right?
It might.
I think so. It's a huge. No, it's not. I don't think it's one of the war problems.
No, it's just a lot of work, but it's all basic principles. It's all stuff that you should remember. Like the PV equals nRT, very important that you remember this. Okay, so we do that. 61.9, so roughly about 62 grams. 62 grams per mole. So we know our empirical formula says it's C1F1. So C1F1 is 12 plus 19, which is roughly 21. No, 31. So about 31 grams. Okay? The molar mass is 62. So what we do, we just divide this by 31, and it equals 2, which means that this guy needs to be doubled in order to reach the molar mass. So this guy is really going to be C2F2. This is our first part. This is the molecular formula. Okay? So now we're going to go ahead and do that. So C2F2.
That's the first part.
That's our molecular formula. That's what we would plug in there.
C, and then it's 2.
Okay? So now we got to figure out how this thing connects. So we know that...
Why is it not letting me?
Because you're clicking on letters or words.
Right here.
Oh, here, just do this. Do control. Wait, that is it working? You might have to redo it. There we go. Okay, so yeah, it's acting weird. Must be your keyboard. Yeah, just do it that way then. Okay, make sure to make that big. Okay.
Not letting me.
It's not letting you. Oh, there you go. Okay. So the next step is to figure out what the shape of this guy is. Okay, so we know that for the most part, molecules like to have symmetry. Okay, so we're going to assume that the carbons are in the middle, because if we look at each one, we're basically looking at it this way. We see carbon, carbon, probably a fluorine, and then a fluorine.
Yeah.
Okay, now fluorine we know has 1, 2, 3, 4, 5, 6, 7. Carbon has
4.
1, 2, 3, 4. Carbon has 1, 2, 3, 4. Fluorine has 1, 2, 3, 4, 5, 6, 7. Okay, so we can assume that a bond is going to be made between, only one bond can be made with the fluorine. Mm-hmm. So fluorine is going to make that one bond with the carbon. Okay, and here we can only have one bond made with the fluorine.
Mm-hmm.
Then here we assume, okay, there's going to be at least one bond there. But now carbon
Needs 3 bonds.
needs
4.
3 bonds. So we're going to take this one and this one, form another bond, and these two and form another bond.
Mm-hmm.
So that's our structure. We got fluorine with a carbon, triple bonded to a carbon with a fluorine.
Okay.
And that works because it obeys the octet rule and it stays with the correct amount of valence electrons.
Okay. In chlorine, do we add all the dots? Yeah, right?
Only if it says to show valence electron, I mean lone pairs.
Do the Lewis structuring of the compound. So we don't
Yeah, you don't need to do lone pairs. Okay? Now let's look at this guy. Is this guy, what's his geometry?
Well, it has a 4. It has a double bond. No, wait. Would it be like triangular or something?
Triangular?
Uh-huh.
Let's take a look at this. So we got this guy right here and this guy right here. Okay, trigonal would be if you had something with 3 things attached to it.
Yeah.
Here we got, how many things is attached to this carbon?
1, 2.
1, 2. How about this carbon?
2.
1, 2. Okay, so we got 2 things attached to it. So it's not going to be trigonal because it would need 3 things. It's not tetrahedral because it would need 4. So yeah, this guy is linear. If we look, this angle right here is going to be a perfect 180. As well as this angle right here. It's going to be a 180. So we would call it linear.
Okay.
And then if we were looking at this guy over here, let's look at the polarity. So we know there's polarity because we're looking at different types of atoms. The thing is that if they were similar atoms, there would be no polarity. Or if it was a C and a H, we would say that there's no polarity because it's too small to matter. So here we see that there's going to be a movement between the carbon and the fluorine. The fluorine, by looking at the periodic table, we can see that this guy is more electronegative, meaning the carbon is going to be slightly positive. And it's going to be the same over here, negative, and then we've got positive right there. So we're going to see a movement from there to there, and a movement from there to there. So the question is the molecule itself polar? Not just the bonds, because this is a bond. The bond is polar, but is the molecule polar?
Paul, is it like based on that? No.
No.
Because like yeah, they're polar like the bonds, but they stop each other.
Exactly. They cancel each other out. So this guy is non-polar.
Okay.